On this 2015-2025 F150 with the 3.5 EcoBoost, P0171 means the PCM may be seeing bank 1 as too lean, and it may be adding fuel until the adaptive fuel strategy reaches its rich limit. The truck may have a check engine light, may idle rough, may hesitate, or it may drive fairly normal depending on when the fault shows up. Broadly, this can come from possible unmetered air, vacuum or PCV issues, exhaust or oxygen sensor circuit concerns, fuel delivery problems, fuel quality, EVAP purge flow, injector issues, or related wiring and connector faults. The key is not to guess. Start with the basic system checks, keep the captured operating conditions, and follow a structured diagnostic approach. First, check what codes are present. If P0171 is part of a group of fuel control or oxygen sensor related codes, use those codes as context, but keep this diagnostic path focused on the bank 1 lean concern. If other unrelated codes are present, check what they mean first. Next, record the ECT or ECT1 value from the captured conditions so you can recreate the concern. Do not clear the codes and do not reset KAM yet, because that learned information is part of the diagnosis. With the ignition off, do a careful visual inspection before running tests. Check for intake restrictions, air filter and housing problems, leaks from the MAF sensor to the intake manifold, damaged or loose intake tubes, throttle body hose issues, obstruction, sludge at the throttle plate, cracked or misrouted vacuum hoses, damaged vacuum tees, EVAP hose concerns, intake manifold or gasket leaks, EGR leaks, PCV system integrity, and the correct PCV valve part number if equipped. Also inspect for exhaust leaks at flanges and gaskets, oxygen sensor wiring or connector contamination and damage, cross-sensor wiring, and anything as simple as an oil dipstick tube or oil fill cap not seated correctly. If you find a vacuum leak, move to vacuum leak repair verification. If you find another clear fault, repair it as needed, clear the PCM codes and rerun the check. Next, run the relative injector flow test with the scan tool. If that test is not available, continue as though the test passed. If the test fails, install a new fuel injector for the injector in question, reset KAM, clear the PCM codes and repeat the check. After that, run the power balance test. Again, if the scan tool routine is not available, continue as though it passed. If power balance fails, use the injector type called for by the vehicle. Port fuel only gets a new fuel injector, and the other path gets a new direct fuel injection fuel injector. Then reset KAM, clear the PCM codes and repeat the check. Now check whether EVAP purge is pulling vapor when it should not. Use the scan tool EVAP purge check when it is available. If it is not available, with the ignition off, install the fuel filler cap or remove the supplemental refueling adapter. Then turn the ignition on and monitor FTPV. Record the FTP value. Start the engine. Command EVAP PID to 0% and command EVAP PID to on 100% duty cycle. The check passes if the EVAP purge check passes, or if the FTP PID voltage stays within 0.5V of the recorded PID voltage value within 30 seconds of closing the EVAP purge valve. If it does not pass, install a new EVAP canister purge valve, clear the PCM codes, and repeat the check. For P0171, if purge checks good, move into the vacuum leak split. Start the engine and monitor CHT, ECT1, IAT, LOMFT1, SHRTFT1, LOMFT2, and SHRTFT2. Recreate the captured conditions. When the captured ECT value is not available, use the monitor gate of between 82 degrees C, 101 degrees C, 180 degrees F, 215 degrees F, with IAT less than 46 degrees C, 115 degrees F. Add long-term and short-term fuel trim together for each bank at idle. Then raise engine speed to 3,500 RPM for 10 seconds and calculate total fuel correction again. If the total fuel correction difference between idle and 3,500 RPM is less than 15% of the total value at idle, the path moves toward fuel pressure. If it is not, go after a vacuum leak. In this same area of the routine, the MAP check is simple. Key on, monitor MAPV, record the MAP voltage, start the engine, and record it again. The question is whether the PID value changes. If it changes on the P0171 path, continue toward fuel pressure. If it does not change, stop and diagnose the MAP signal path instead of guessing. To locate the leak, find the vacuum tees for the intake air and PCV systems. Start the engine, monitor SHRTFT1 and SHRTFT2, and restrict vacuum lines one at a time for 30 seconds. Do not clamp or pinch a hard plastic hose. Use a vacuum cap or equivalent to restrict it. If the short fuel trims drop greater than 15% when a hose is restricted, that branch has the leak. If the hose restriction does not show it, inspect the intake air system, intake manifold, and intake gaskets for a vacuum leak. After repair, start the engine, recreate the concern, compare the before and after SHRTFT values, and confirm the drop is greater than 15%. If it is not, a vacuum leak is still present, so go back through the leak locating steps instead of guessing. Before the fuel pressure side, if the path calls for the universal oxygen sensor pump current circuit check, turn the ignition off, disconnect the universal HO2's connector and the PCM connector, then check the specified 3.5 EcoBoost circuits between the sensor connector and PCM connector. The resistance needs to be less than 5 ohms. If it is not, repair the open circuit, reset KAM, and repeat the check. Then check fuel pressure. Use fuel pressure safety precautions, because the system may still be pressurized with the engine off. Relieve pressure. Connect a mechanical fuel pressure gauge, pressurize the system. Start the engine, let pressure stabilize. Then use the scan tool fuel pump command to obtain maximum fuel pressure. If pressure is not in range for the vehicle being diagnosed, move into the fuel pressure diagnostic path instead of replacing parts. If pressure is in range on this 3.5 EcoBoost path, check for a biased FRP sensor by turning the ignition off, disconnecting the fuel injection pump connector, starting the engine, monitoring FRP, and commanding fuel mass die to maximum. The FRP PID should be between 345-827 kPa 50-120 psi. If it is not, install a new fuel rail pressure sensor, clear the PCM codes, and repeat the check. There is also an FRP to FLP comparison in this part of the routine. With the fuel injection pump connector disconnected and the engine running, monitor FRP and FLP. FRP should be within 138 kPa 20 psi of the FLP value. If it is not, install a new fuel rail pressure sensor, clear the PCM codes, and repeat the check. Next, reconnect the fuel injection pump connector and check pressure stability. Turn the ignition on, command the fuel pump to maximum pressure, command the pump off, let pressure stabilize, record it, and watch for 10 seconds. Pressure should remain within 34 kPa 5 psi of the recorded reading after 10 seconds. If it does not, inspect the fuel tank lines and filler pipe for an external fuel leak. Repair any leak found, reset KAM, and repeat the check. If no external leak is found, move into the appropriate fuel leak down diagnostic path. If the fast leak down passes, continue watching for 1 minute. The slow leak down passes when fuel pressure remains within 34 kPa 5 psi of the recorded reading MRFS, or greater than 275 kPa 40 psi. ERFs, after 1 minute. If it fails, continue with the fuel leak down diagnostic path. On branches that call for it, check for electrical noise before moving on. With the ignition off, inspect the CKP sensor harness for routing, alterations, incorrect shielding, or interference from other systems. Also pay attention to radio frequency interference and excessive audible generator noise. If a concern is present, repair it, clear the PCM codes, and repeat the check. If fuel pressure stability is good, check the fuel itself. For the ethanol separation check, use a 200 ml beaker with 5 ml of clean water. Drain 22 ml of fuel into an approved clean container. Pour 20 ml of fuel into a 25 ml graduated cylinder. Then add enough water to bring the total volume to 24 ml. Stopper it, shake it, and let it separate for approximately 3 minutes. Record the separation level where the ethanol and water mixture meets the gasoline. If the fuel does not separate, treat it as contaminated fuel, replace the contaminated fuel, clear the PCM codes, and repeat the check. To calculate ethanol percentage, take the recorded separation level, subtract the amount of water added, multiply the result by 5, and record that percentage. For example, 14 minus 4, then multiply by 5 to equal 50. The percentage of ethanol in the fuel is 50%. On a flex fuel vehicle, compare FFINF to the calculated ethanol percentage. It should be within 20% of the calculated percentage of ethanol. If it is not, reset KAM, start the engine, monitor FFLRND, and drive approximately 11.3 km 7 miles, or until FFLRND indicates yes. Then cycle the ignition and compare FFINF again. If it is now within 20%, return the vehicle and advise correct fueling practices. The customer should continue using the same fuel for the next 2-3 refuels. If the PCM still cannot learn the correct percentage, a fuel system concern may be preventing correct learning, so continue with fuel system diagnosis. On a non-flex fuel vehicle, if the calculated ethanol percentage is less than 25%, continue with the fuel system diagnostic path for this lean code. If it is not less than 25%, repair as necessary. Advise the correct fuel type, reset KAM, and repeat the check. If this path reaches the oxygen sensor and airflow validation area, keep it clean and connector focused. With the ignition off, disconnect the universal HO2's connector and inspect for pinched, shorted, or corroded wiring and pins, oil or water contamination, cross-sensor wires, or a contaminated or damaged sensor. If a concern is present, repair as necessary, clear the PCM codes, and repeat the check. Where the path continues into MAF operation, monitor RPM, MAF-V, MAF-HC, and MAF. Run the engine up to 500 RPM for 5 seconds, return to idle, and repeat. The idle MAF value should be within 30% of the normal PID value. Then connect the universal HO2's connector. Let the engine enter closed loop. Monitor RPM, ECRAT 11, and ECRAT 21. Raise engine speed to 2,000 RPM for 1 second, and return to idle. The oxygen sensor feedback should change from greater than 1 to less than 1, or from less than 1 to greater than 1. If it does, the concern may not be duplicated at that time. If it does not, continue into the connector and sensor operation checks instead of condemning a part too early. The same shared fuel control routine also has branches for rich side crankcase fuel leakage and oxygen sensor circuit checks. If that branch applies, start the engine at normal operating temperature, monitor LOMFT 1, SHRTFT 1, LOMFT 2, and SHRTFT 2, and record the values. Then turn the ignition off, disconnect the PCV line at the intake manifold, temporarily plug the intake manifold port, restart the engine, let it idle at normal operating temperature, and compare the current trims to the recorded trims. The question is whether the fuel trims shift and the rich condition is no longer present. For oxygen sensor monitor codes that show up with the engine running, run the engine at approximately 2,000 RPM and hold it for 3 minutes. Then check whether those sensor monitor codes are present. If they are, diagnose the suspect sensor circuit. With the ignition off, disconnect the PCM connector and the suspect HO2's connector, then check the HO2's harness for shorts between circuits. Those resistances should be greater than 10 k ohms. Next, check the HO2's circuit for opens. Those resistances should be less than 5 ohms. Then turn the ignition on and check the HO2's circuit for a short to voltage. Any voltage present means repair the short, clear the PCM codes, and repeat the check. If there is no short to voltage, reconnect the PCM and HO2's connectors, start the engine, let it idle for 2 minutes, and monitor the downstream HO2's output voltage. The PID voltage should be less than 1.5 V. If it is not, Continue to the correct HO2's operation check. If the routine gets to the correct PCM operation check, disconnect all PCM connectors, inspect for pushed-out pins and corrosion, then reconnect all PCM connectors and make sure they seat correctly. Verify whether the concern is still present. If it is still present at that point, install a new powertrain control module. If it is gone, the system is operating correctly at that time, and the concern may have been caused by a loose or corroded connector. For correct universal HO2's operation, turn the ignition off. Disconnect all PCM connectors and the universal HO2's 11 and HO2's 21 connectors. Inspect for pushed-out pins and corrosion. Reconnect everything fully seated. Reset KAM and verify the concern. If the concern is still present, install a new universal HO2, reset KAM, and repeat the check. For correct HO2's operation, do the same connector inspection and reseating process with HO2's 12 and HO2's 22. Reset KAM and verify the concern. If the concern is still present, install a new HO2, reset KAM, and repeat the check. Keep verification separate from testing. After any repair, clear the PCM codes when the step calls for it. Reset KAM when the step calls for it. Recreate the captured operating conditions and confirm the code stays gone. The takeaway on P0171 is simple. Prove whether bank 1 is lean because of air, fuel delivery, fuel content, purge flow, injector contribution, or sensor feedback before replacing parts. For more diagnostic training, visit stepdiagnostics.com.